Welcome to the solutions to the AP Physics Newton Laws problem set numbers 8, 9, and 10. Let's go ahead and get started with number 8. It says, if a car is traveling westward with a constant speed of 20 meters per second, so that's V, and it would be average speed there, what is the resultant force acting on it? So they want the F. Really what they want, when you hear resultant force, it's the same thing as net force. Okay? So we take a look at our car over here, and if we did our free body diagram, there obviously has to be a force forward on the car to keep it moving. And it's traveling to the west. And our motion arrow indicates that it's traveling to the west under constant speed. So we'll label that with a V. Well, if it's moving at constant speed, what does that mean? This means it is not accelerating. Well, if it's not accelerating, that means m times a in sigma f equals ma is 0. Therefore, the summation of forces is 0. So that means there has to be some kind of resistive force. We'll just label it Fr here for resistive force. That is equal and opposite of the force causing it to go forward. The summation here would be F minus Fr. Remember that the direction of motion is positive, equals 0. So F equals Fr. Some people get confused by this and wonder, well, then why is the car even able to move? It's not about the car. It's not about the fact that the car is able to move or not. It's about the fact that the car cannot accelerate. And you have to remember there are two conditions that can meet that requirement for not accelerating. That is at rest or moving at constant speed. And this problem covers that scenario. Okay? All right, number 9. If gold were sold by weight, would you rather buy it in Denver or in Death Valley? If it were sold by mass, in which of the two locations would you prefer to buy it and why? This question gets at something that we need to be careful about and kind of actually nitpicky about in this class, and that's the difference between weight and mass. Mass is the amount of matter an object possesses, and weight is the pull of gravity on that mass. If we just take the equation F equals ma, we can tweak that and change it to be gravity specific. So the force due to gravity equals m times the acceleration due to gravity. Sometimes what you see also abbreviated here, instead of using Fg, we'll just use little w. And that's kind of the preference in here, though it is just a preference. You can do whatever you want as long as you have a symbol that represents force due to gravity, also called weight. W equals mg. So what this is getting at is, if gold were sold by weight, would you rather buy it in Denver or in Death Valley? Well, if it's bought by weight, that price is going to depend on the mass of the gold times the acceleration due to gravity at that location. Well, the G value in Denver is going to be less than the G value in Death Valley. And I'll just use dV there. And the reason for that is because Denver, may know, it's called the Mile High City, is much further from the center of the earth than Death Valley. So because Death Valley is closer to the center of the earth, the acceleration due to gravity is going to be greater than the acceleration due to gravity in Denver. So if you're going to buy this by weight, buy it in Denver because you would pay a cheaper price. But if it were sold by mass, then it's not going to matter. And that's how they should sell it if they want to make sure that they don't get ripped off one way or the other. So if you sell it by mass, make sure that you do that so that if it's sold by mass, you're paying the same in either location because you're paying for the amount of matter it possesses. Okay, now let's go over number 10. This asks us to analyze the motion of a rock dropped in water in terms of its speed and acceleration as it falls. Assume that a resistive force is acting on the rock that increases as the velocity of the rock increases. Okay, so here's our rock in the water. Let's do a free body diagram for the rock in the water. And of course, the easiest one to label is the weight down. And something that we do with this, yes, you could put FG or you could put W, but often what we do for this force, because it's the weight of the object, is we just substitute, and I'll erase these two, and we just put mg. Okay, so, and again, that's a preference thing. That's what you're going to see modeled in here. Doesn't mean you have to do it that way. So we have the weight down, and we're told that we have a resistive force. Again, we'll put this as Fr, acting up on the rock. And we're told that that resistive force increases as the velocity of the rock increases. So if we were to draw a motion arrow, which obviously the motion is down, it's falling, what we would say about that is that the rock starts out accelerating, but then moves at some point where the resistive force becomes equal to the weight of the object. Let me demonstrate that over here with our Newton's second law approach. So again, we start out with sigma F equals ma. When this rock, we're going to go ahead and label that now, reaches what is called terminal velocity, the falling velocity that remains constant after some period of time. What that means is then the object is not accelerating. So the product of m and a is 0. What would be the summation here? Well, this would be mg down in the direction of motion minus Fr equals 0. So this shows that if the rock is traveling at terminal velocity, constant velocity that is, that the weight and the resistive force have to be equal to each other. Okay, so I can't imagine that we could analyze the motion of this rock any more accurately than that and more thoroughly than that. Alrighty, more practice with Newton's second law problems in class tomorrow.